In this video, we're going to take a look at the formal definition of a limit. We will do that by first looking at an informal definition, but then we're going to jump straight into the formal definition. So, informally, if f of x becomes arbitrarily close to a single number L, right, so our function f of x is getting closer to L as x approaches c from either side, then we say the limit of f of x as x approaches c is L. And we write it in this way. So that's what we mean, right? So if our function value is getting closer and closer to some number L whenever x gets closer and closer to some number c, then that limit of f of x as x approaches c is equal to L. Now, saying it informally, while that's not necessarily simple, when we formalize it, it does feel maybe a little bit trickier. But let's take a look at that. And so here is our formal definition of a limit. And so our formal definition, the limit as x approaches c of f of x equals L means that for each epsilon greater than 0, there is a delta greater than 0, right? So this is epsilon. This is delta. For each epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus c is bigger than 0, but smaller than delta, then the absolute value of f of x minus L is going to be less than epsilon. So what that's saying is, here, this absolute value is a distance, the distance between x and c. If it's more than 0, but less than some value delta, and we'll think about delta being really small, then we can guarantee that the distance between f of x and L is less than some number epsilon. Right? So how close do you want to be? Well, pick that number epsilon, and I will be able to tell you some value of delta that will say, as long as we're within delta units of c, I will guarantee you the function will be within epsilon units of L. That's the formal definition. That is a definition that in calculus is a valuable definition to know, to learn, to have down. I would encourage you to have a thorough understanding of that. Yeah. I'm going to write that definition one other way, or show that definition in one other way, and that is a very mathematically heavy notational way, and that is right here. So in a symbolic notation, we would write this definition up here in this way. So the limit as f of x, the limit as x approaches c of f of x is equal to L. So this means if and only if and only if, that upside down looking A means for every, so if and only if, for every or for all epsilon greater than 0, the backwards looking E means there exists the limit as x approaches c of f of x is equal to L if and only if for every epsilon greater than 0, there exists a delta greater than 0, such that zero less than x minus c less than delta. This double arrow just in a single direction implies that the absolute value of f of x minus L is less than epsilon. So that's our formal definition of a limit. Now, I know that there's a lot there, so let's see if we can unpack that a little bit more. So, We should think of epsilon, so this is just our definition rewritten. We should think of epsilon as being some really small positive number. And for every single epsilon we could pick, there is some other corresponding small positive number delta, such that if x is within delta units of c, f of x is guaranteed to be within epsilon units of L. And so let me try to draw this graphically. So if we have some value c out here, and that function has some limit L, my claim is it has a limit L, and I want to be certain that we are within epsilon units of L. Then if we go epsilon units below L, so L minus epsilon, and epsilon units above L, L plus epsilon, we can force that, we can ensure that by figuring out a corresponding value of delta. So we have C plus delta, C minus delta. So as long as we are within delta units of C, if we're in this window somewhere here, we're guaranteed that no matter what function value we get out, we are going to be within epsilon units of L. If you make that window smaller, then if you make that value of epsilon smaller, we just make this window smaller. But no matter what value you might choose, as long as it's not 0 and is a positive value, we can always guarantee this. So that is the idea. Now there's a little bit here that I've hand-waved over these values of delta on either side. They don't have to be exactly the same number. And so there are some strange things that can happen. We will wait and look at that sometime in the future. For now, let's assume that they are equal, but they don't have to be. You could have some value on the left and right, and then you would just pick delta to be the more restrictive of the two values, right? Whichever is the smaller of the two values. So if we could go 0.7 on this side, but only 0.3 on this side, we'd just say, oh, well then let's just stay within 0.3, and up above, I might not be able to get all the way up to L plus epsilon, but I'll still be less than epsilon away from L. All right. In our next video, we are going to take a look at finding this value of delta based on based on epsilon. All right, we will see you there.